Now, what if we were to reverse that? How much information is needed for the chemicals to become a live cell? So we reverse the equation. You have dead chemicals plus information plus some other stuff will give you life. Now, what we want to point out here is that information needs to be added carefully at the proper time. If you give the wrong gene sequence at the right time, you wind up not fulfilling the protein or not creating the protein. If you wind up the gene expression of a protein that is the wrong protein, then you again don't wind up with life. You need just the right amount of genetic information, and it needs to be free of errors. So why are we saying this? Well, if you remember from our analogy about a space station, the very first cell needs to have information injected into it, and it needs to be all of the information needed to build all of the analogous robots and factories and power plants and data centers so that that space station could actually operate properly. And this needs to be created all at once. And then once it's created, it can be replicated to form another cell. The point that I'm trying to bring out here is that it's not just information. It's information at the right time, in the right place, with the right amount, that's error-free for all of the things that need a cell to function. So the approach we'll take in looking at this scientific model is to estimate the probability of this happening. We're going to ignore a lot of stuff. We're going to just focus on the information. We're going to start with a simple problem, and we're going to use the most favorable conditions and assumptions. Why are we doing this? Well, if the simple problem is unsolvable, if a simple system can't occur, then a much more complex system can't occur either. So this is a step in trying to model all of the complexity, but we don't need all that complexity to find out, is it possible for undirected macroevolution to add the information for the first cell?